When you read a sentence, you don't process each word in isolation. Your understanding of each token is deeply conditioned on everything that came before it. Traditional feed-forward networks have no mechanism for this. Each input is processed independently, with no persistent state. Recurrent neural networks solve this by introducing a loop. At each time step, the network takes an input x_t and the previous hidden state h_t1 and produces a new hidden state h_t. When you unroll this loop across time, you get a chain of identical modules, each one a copy of the same network, passing information forward. This chain-like structure makes RNNs a natural fit for sequential data, language, time series, audio, anything where order matters. And for about 2 decades, this was the dominant paradigm for sequence modeling. Here's where things break down. Consider a simple case, predicting the word sky in the clouds or in the blank. The relevant context is just a few steps back. Vanilla RNNs handle this fine. But now consider, I grew up in France. I went to school there. I studied literature. And then much later, I speak fluent blank. The answer is French, but the relevant context is dozens or hundreds of steps in the past. Hochreiter showed in 1991, and Bengio formalized in 1994, that the gradient signal during backpropagation through time decays exponentially with the number of time steps. The core issue is the repeated multiplication by the Jacobian of the state transition. If the spectral radius of this Jacobian is less than 1, which it typically is after training with tan nonlinearities, then gradients vanish. The network can't learn to connect distant cause and effect. This isn't a training trick problem. It's a fundamental architectural limitation. Long short-term memory networks, introduced by Hochreiter and Schmidt-Huber in 1997, were designed explicitly to solve the vanishing gradient problem. Let's compare the architectures side by side. A standard RNN module is simple: concatenate the previous hidden state and current input, pass through a single tan layer, output the new hidden state. One nonlinearity, one learnable transform. The LSTM module is dramatically different. It contains 4 neural network layers, 3 sigmoid gates and 1 tan layer, interacting through a carefully designed information flow. But the key structural innovation isn't the number of layers. It's the introduction of a separate cell state, C_t, that runs alongside the hidden state. This cell state is the mechanism that allows information to persist across long sequences. The hidden state h_t is what gets output to the next layer. The cell state C_t is the internal memory. And the gates control how information moves between them. Look at this diagram. The cell state runs horizontally across the top of the LSTM, like a conveyor belt. And here's the critical insight: the operations on the cell state are linear. It's modified only by pointwise multiplication and pointwise addition. No matrix multiplications, no nonlinearities applied directly to the cell state itself. Why does this matter? Because the gradient of addition with respect to its inputs is 1. When you backpropagate through the cell state path, gradients flow nearly unchanged. This is the gradient highway that makes LSTMs work. The gates, these sigmoid-based mechanisms, are what control the traffic on this highway. A sigmoid output of 0 completely blocks information. An output of 1 lets everything through. They're learned, differentiable binary switches that determine what gets written to memory, what gets erased, and what gets read out. Let's walk through each gate. The forget gate is the first computation at each time step. It takes the previous hidden state h_t1 and the current input x_t, concatenates them, and passes them through a learned affine transform followed by a sigmoid. The output f_t is a vector of values between 0 and 1, with the same dimensionality as the cell state. Each component of f_t independently controls whether to keep or erase the corresponding dimension of the cell state. When f_t of I equals 1, the ith component of the cell state is fully retained. When it equals 0, it's completely forgotten. Here's a concrete example. Suppose your modeling language in the cell state is encoding that the current subject is feminine singular. When a new subject appears, say a masculine noun, the forget gate needs to clear out those gender and number features to make room for the new information. This is a learned behavior. The network discovers which cell dimensions encode which features and learns when to reset them. The input gate determines what new information gets written into the cell state. It's a two-part computation. First, the input gate vector I_t, another sigmoid layer applied to the concatenated H_t1 and X_t. This produces values in 0 to 1, controlling which dimensions of the cell state receive updates. Second, the candidate values C_t, a tan layer applied to the same concatenated input, producing values in -1 to 1. The tan is important here. It means the candidate can both increase and decrease cell state values, allowing bidirectional updates. The product I_t times C_t gives you the actual update. The input gate selects which dimensions to write, and the candidate values provide what to write. In our language model example, the input gate would activate for the dimensions encoding subject properties, and the candidate would write the new subject's gender and number features. Now we combine the forget gate and input gate to actually update the cell state. The equation is elegant. C_t equals F_t Hadamard C_t1 plus I_t Hadamard C_t. Let's unpack this. The first term, F_t times C_t1, is the selective forgetting. Wherever the forget gate is near 0, the old cell state gets zeroed out. Wherever it's near 1, it's preserved. The second term, I_t times C_t, is the selective writing. New candidate values are written only where the input gate allows. And notice, this is a purely additive update on the dimensions that are retained. F_t times C_t1 plus the new information. This additive structure is what creates the gradient highway. During backpropagation, the gradient of C_t with respect to C_t1 is simply F_t, a diagonal matrix of values between 0 and 1. As long as the forget gate doesn't consistently output 0 for any dimension, gradients flow backward through time. This is the fundamental mechanism that solves the vanishing gradient problem. Finally, the output gate determines what the LSTM actually exposes to the outside world. Not everything stored in the cell state needs to be outputted every time step. The output gate vector O_t is computed the same way as the other gates, sigmoid of a learned transform of H_t1, concatenated with X_t. The hidden state, which is the actual output, is then computed as O_t times tan of C_t. The tan squashes the cell state values to -1 to 1, and the output gate selectively reveals dimensions. This separation of storage and output is powerful. The cell state can maintain long-term memories, like the subject of a paragraph, without constantly exposing that information. The output gate opens only when that stored information is relevant to the current prediction. For instance, the cell might always store that the subject is plural, but the output gate only activates those features when the network needs to generate a verb that requires number agreement. The standard LSTM spawned numerous variants. Let me highlight two important ones. First, peephole connections, introduced by Jers and Schmid-Huber in 2000. In the standard LSTM, gates CH_T1 and X_T but not the cell state directly. Peephole connections add C_T1 as an additional input to the gates. This lets gates make decisions based on what's actually stored in the cell, not just the filtered output. It's particularly useful for tasks requiring precise timing, like rhythm detection. Second, coupled forget input gates. Instead of having independent forget and input gate decisions, you constrain them, F_t equals 1 minus I_t. This enforces a complementary relationship. You only forget when you have something new to write. This reduces parameters and can improve training stability. Now, an important empirical result. Greff et al. In 2015 did a systematic comparison of LSTM variants and found that no single variant consistently outperforms the standard architecture. Josefovich et al. Tested over 10,000 architectures and reached a similar conclusion. The standard LSTM is a remarkably robust design. The most popular LSTM simplification is the gated recurrent unit, introduced by Cho et al. In 2014. The GRU makes two key changes. First, it merges the cell state and hidden state into a single vector. There's no separate memory. H_t is both the internal state and the output. Second, it uses 2 gates instead of 3, a reset gate R_T and an update gate Z_T. The update gate plays the role of both the forget and input gates. The update equation is H_T equals 1 minus Z_T times H_T1 plus Z_T times H_T. When Z_T is near 0, the old state is preserved. When it's near 1, the new candidate replaces it. The reset gate controls how much of the previous state contributes to the candidate computation. When R_T is near 0, the candidate is computed as if starting fresh. The result is fewer parameters, faster training, and, on many benchmarks, comparable performance to full LSTMs. In practice, the choice between LSTM and GRU is often empirical. GRUs tend to work better on smaller datasets where the reduced parameter count helps with regularization. LSTMs didn't just solve a theoretical problem, they enabled an entire generation of breakthroughs. Machine translation, speech recognition, image captioning, handwriting generation, essentially every major result in sequence modeling from 2014 to 2017 was achieved with LSTMs. But the story doesn't end there. The attention mechanism, introduced by Bodnow et al. In 2014, originally as an addition to LSTM encoder-decoders, provided a complementary solution to long-range dependencies. Instead of relying solely on the cell state to carry information forward, attention lets the decoder look back at any encoder position directly. This raised a provocative question: if attention can provide direct access to distant context, do we need the recurrence at all? Vaswani et al. Answered in 2017 with the transformer, attention is all you need. But here's the key insight: the principles that make LSTMs work, gating, cell state highways, selective memory, these ideas didn't disappear. They evolved. Understanding LSTMs isn't just historical appreciation. It's understanding the foundational mechanisms of learned memory and information routing that underpin all modern sequence architectures.